Good morning, Denise.
Good morning, Mr. King.
How are you?
I'm doing good. How are you?
Good, thank you. I hope my voice sounds lousy as ever. I hope it sounds better. Not really, huh?
It's about the same, but it's all right.
Okay. Okay, so welcome back, and we have 3 more lecture sessions, counting this one. So that's not bad. And today we are going to ideally finish 9.3. There's a short discussion there. And then I think it's in everyone's best interest to delay on 9.4, the limit and direct comparison series test, and go to 9.5, which is the alternate series test, and 9.6, which is the ratio and root test for series. And those are, especially the last two, 9.6, are incredibly short. And so is 9.5, really. And the remaining discussion on 9.3, there's one more test, and you'll see quickly that it's a very quick test. It's the fastest one, even maybe faster than the geometric one. Okay, but anyway, so here we go. I already wrote down a problem on number 8, even though I had mentioned that that you shouldn't have any issues with number 8 in terms of following the directions and using the integral series test. So I'm going to use this example, this exercise, to help understand the next series test we're going to learn, and so that's where we are. Okay?
Okay.
So let's look at number 8, and I'm going to go to my notebook. And again, if you want to take a picture of this or look at the video later, I'll leave it up to you, each person, but because for time's sake, I already wrote down problem 8, and I'm going to show everyone how to do number 8 with the integral test, which is just a review of what we talked about on Monday. So it gives us a chance to look at the integral series test again, but leading us to where I want our minds to be to learn the next series test, okay?
Okay.
Okay, so you can see my notebook, everything's fine?
Yes.
Okay, so number 8 is right here, and we have this formula right here, 1 over n to the 4th, so that's the formula of the sequence. And of course, this means to add them up from the first, from n equals 1 forever, which means this is a series, or we can say infinite series, and we want to know if we start to add up these terms forever, do they converge to a single finite number or not? Yeah? Diverge. So let's proceed. And of course, if you have any questions, let me know. So let's see here. So here are the first terms. We put a 1 in, and we get 1 to the 4th power is 1, so 1 over 1. All the numerators are going to be 1 because of the formula right here, of course. And if we put a 2 in, 2 to the 4th power would be 16, 3 to the 4th power would be 81, and so forth. And our first step is always to check, well, are these individual terms, as we go out forever, are they getting smaller and smaller, closer and closer to 0? And so we can look at that visually or observationally. We could look at put these numbers in a calculator and so forth, or just take the limit. And if we do take the limit of the formula of the sequence, then we have 1 over n to the 4th, and the limit as n approaches infinity. So 1 over a bigger and bigger number, of course, gets closer and closer to what?
To 0.
To 0. So we can say converges to 0. Okay. And good morning, Brian.
Good morning.
How are you?
Good, good. And yourself?
Good, thank you. We're looking at problem 8 from 9.3, and we're going to use this problem to put our minds, or I want them to be mathematically, to introduce the next series test, okay?
Okay.
And if you want to take a picture of this or later look at it on the video, because I already wrote down the problem, I'm just kind of quickly going through it because this is a little bit of review from the Monday's session, and also for time we can go faster and get into the new part. Okay. So we just showed that the limit of the individual terms of the sequence does converge to 0, and therefore coming back over to this location, therefore this sum, the sum of all these terms forever and ever has a chance at least to converge, and so that's what I have written right here. So the series has a chance at converging, and now we need to explore further using one of the, I kept saying 8 or 9, it kind of depends if there's one if we want to name it or not, so 8 or 9, but I think we'll say officially 8, but there's another one that is very useful that I will mention, but it may not be on the author's official list, even though it's in the chapter. But anyway, and we only know to a series test at the moment after the first step, which is really the nth term test for divergence, but we got the limit to be 0, so that's why we know we have to continue exploring, and we're not simply done by using the nth term test for divergence. So we're exploring further with, so it has to be at the moment either geometric or the integral series test. If we divided 1 over 16 divided by 1, well, that's 1 over 16, that's kind of easy to see. And if you divide 1 over 80, if you take 1 over 81 and divide it by 1 over 16, you're not going to get the same ratio. So there's no common ratio, and therefore it's not geometric. The only other series test we know is the integral series test, and that's what it actually tells us in the directions, is to use it. And anyway, we could know that because if we change this sequence formula to a function, f, so it would be the function f of x, 1 over x to the 4th would be the function. Oh, I wrote it over here. The conditions for the function 1 over x to the 4, knowing that we're going to try to use the integral series test. Provided the 3 conditions are met, which we're going to show that they are, then and also if we are able to integrate this with relative ease, then the integral series test is perfectly a great test to use to determine if the series up here, that infinite sum, converges or diverges. So, and the integral of would be from 1 to infinity, because that's where we're going here, becomes, this is an improper integral, and the design of the integral series test is if the 3 conditions are met regarding the function, then knowing if we're able to integrate the function, then evaluate the limit, and if this improper integral converges or diverges, well, it's going to have to converge or diverge, then we will know what the actual sum of all these terms do. They'll do the same thing, which is converge or diverge. So that's our logic behind the integral series test. And 1 over x to the fourth becomes x to the negative 4. And that's a simple power rule to be able to integrate. So we'll have no trouble at all being able to integrate this function 1 over x to the fourth. So thus, this is a legitimate series test that can be used. Is this general idea making sense to you guys?
Yes.
Yes. Yes.
Okay, so let's go back to the conditions for the integral series test, which is to analyze the function. So instead of the sequence formula, a sub n equals 1 over n to the fourth, we convert it into a function. F of x is 1 over x to the fourth. And then we have to have these three conditions met. And we can do it, it could be done more formally. We are doing it informally at this point, which is just to look at the sketch of the graph. So if we were to graph this function on Desmos, there's actually another piece over here. I should be careful. No, it's up here. But we don't need that piece because we're only interested in for starting at n equals 1 or x equals 1, because that's where this sequence starts. So we're not concerned about this other piece. By the way, this other piece is increasing, but we're not concerned about that. So starting at x equals 1, which is right here, and this does go down, decreasing, but it never touches the x-axis. So now the conditions. It is continuous for x greater or equal to 1. There are no vertical asymptote. Well, there is right here, but that's at x equals 0, and we're not concerned about right there. We're only concerned about starting at x equals 1 and greater. So it is continuous, no vertical asymptotes, starting at x equals 1 and onward to the right. There's no holes in the graph. There's no pieces because this is not a piece function. It's only one equation. Well, there is another piece, but it's over here. Anyway, positive. All this graph is above the x-axis, so the range values, the y values, the second dimension values are positive. And it is, visually, you can see that it is decreasing. Although, as you go out here, the slope becomes really, really close to horizontal slope or zero slope, but it is forever decreasing. So, and all of these three conditions are met for x greater or equal to 1, and therefore we can use the integral series test. So again, I'm going more quickly here, even still it takes time, but only because we spent many hours on Monday going over this whole idea. So any questions up to that point?
No.
No.
So now that we can use the integral series test, now we set our minds to integrating the function f of x, which is right here from 1 to infinity. This is an improper integral, so we change this infinity upper limit to b, or whatever other letter, but b is the most popular one, and then take the limit as b approaches infinity of 1 over x to the fourth, but we want to move that up, of course, so that we can use the power rule to anti-differentiate. And then using the power rule, we add 1 to the exponent, and -4 plus 1 is -3, divided by the new exponent, which is division of -3. And, and now I just wrote this 1 over -3 multiplied out in front. This is an invisible times 1 in front. So you can write out in front of this 1 over x cubed, a multiplied 1/3, the -1/3, and the negative can be in the numerator, the denominator, and the front. Doesn't matter. Just in one location. And now evaluate 1 over x cubed from x equals 1 to x equals b. And that's what I have here now. So -1/3, the limit, we're still waiting until we have substituted in the upper and lower limits of integration. And when we put, instead of x cubed, it's going to be 1 over not x cubed, but the upper limit is b, so b cubed. And then the same thing over here, 1 over not x cubed, but 1 cubed. And then clean that up, that's -1/3 still. 1 over 1 cubed is just 1. And now what about when we take the limit? There are no b's in the second part, but there is a b right here. So this part is not affected by when we take the limit as b approaches infinity. So this just stays the 1. And good morning, Joshua. If you can hear me, Joshua, good morning, or Josh. So, so where was I? Oh, sorry. So right here. So when we take the limit as b approaches infinity of 1 over b cubed, then we hope the easiest case is after you take a limit, you get a determining value, a determining limiting value versus an indeterminate. Because if it's indeterminate, then we have to do more work. It could be, we called it unfriendly indeterminate form, and then a friendly indeterminate form. If it's friendly, use L'Hopital's rule. If it's unfriendly, you have to manipulate the expression that gave us the unfriendly indeterminate and can change it so that it'll become a friendly indeterminate and so forth. But the best situation in terms of quickness upon taking the limit is when we substitute and we get a determinate limiting value right off the bat. So let's see. When we put infinity here, oh, I thought I admitted Josh. Something went wrong. Okay. And good morning, Joshua.
Good morning.
How are you doing?
Good, and yourself?
Good. So we're on problem 8 on 9.3, and that was kind of that's a review. So if you want to take a picture of this or go back and look at it later, we're right at the end of problem 8, and we just took the integral, and now we're evaluating it, and now the limit as b approaches infinity of 1 over infinity cubed is infinity. And 1 over a larger and larger number gets closer and closer to 0. So now we can compute, simplify this, and 0 minus 1 is -1 times the -1/3. That's multiplied out in front. That's been waiting, and then we get +1/3 as our single finite number numerical value for the value of this improper integral that was way up here. So that means the improper integral converge, and it converges, which means it is a single finite number, and it just happens to be 1/3. But all we really are worried about is that it converges, and therefore the improper integral converges, and the whole structure of the strategy of the integral series test is if we can use the integral series test, meaning the 3 conditions have been met, there wasn't an easier way to do the problem, then, and if we can integrate the function, then the integral test works fine. And if the improper integral converges, then so will the series. When that means when you add up all the terms. And if the improper integral would have diverged, well, then the series would have diverged as well. That is the conclusion of the integral series test. So therefore, by the integral series test, the series that we started with in this problem, which was way up here, we now know, which means, again, the sum of these individual terms forever will converge to a single, and when I say a single finite number, I'm being redundant. That's what converges means, is it converges to a single finite number, and we would be done. So if we go back to, well, first of all, any questions on that?
No.
No.
Okay, so if we would go back to WebAssign, we would be able to put here, well, here it's converges, and this converge, the improper integral converge to what? To
1/3.
1/3, and then we could check. And because the improper integral converges, then so does this series, and so that would be it. Okay, now I'm using this problem, as I mentioned at the beginning of all this session here, is so that I could use this problem to introduce the next series test. And so that's now where we're going. And so I want to go back to my notebook and share with you what I feel will help you understand what the next series test is. So we just did this whole problem, number 8, which is this sequence. Well, this was the formula of the sequence, but to add up all the terms of the sequence, we call that the series. And the series did converge using the integral series test. Okay. But let's take a second look, I just wrote, at exercise 8, meaning now let's look at it again, but with a different perspective. And here is the perspective I want us to look at. So the terms of the sequence, which we wrote right up here, 1/1, 1/16, and so forth, which we did know individually these terms do get smaller and smaller, converges to 0, which is why we knew this series had a chance of converging, and that's when we need further exploration, which is meaning to use one of the 8 series tests. We just used the integral series test. Now I'm going to propose to you that we could have used another series test, which is the next one we're learning, and then you can tell and decide which one you like better, because both will work, okay?
Okay.
Okay, so here are the same terms of the sequence as we just saw above at the top. Just can't fit it all into the same page unless I zoom out here. But anyway, I hope this is okay. I'm just leaving it though, and not simplifying it to 1/16 to 1/81 and so forth for a reason. So this first term is 1/n to the 4th, but n is what to start out? Where do they want us to start out at? N equals what?
1.
1. So this is n equals 1, or the first term, and it's 1/1 to the 4th. So instead of n, we put a 1. The second term, of course, it's going to be the same. It's the same formula. So it's 1/n to the 4th, and the same with the third term, 1/n value to the 4th, and so on. And forever, and the nth term would be 1/n to the 4th. So just writing it in a slightly different perspective. So, of course, what would this be here, guys? We're going to put in what n value for the second term, then n equals what?
2,
2. And the next one?
3.
3. And so forth. Yeah? Okay. So, when we have this 1 in the numerator, notice there's a 1 in the numerator all the time. And in the denominator, we have a power, and it's the same power. The power is not changing. It's still the 4th power all the way through all the terms of the sequence. The only thing that's changing is what is inside the power, or the base right here. And the base is what's changing, and it's the n. And n is what changes, of course, on the terms of a sequence. This is the first term, so n is 1. This is the second term, so now n is a different number, and it's 2, and so forth. So when we get this form of a pattern for a sequence, 1 over, in the denominator, the same power for every term of the sequence, and inside, which is the base of that power, is what's changing, and it's relative to whatever n is. It's this number here is the same as the n value. So that general form, this general form, a sub n equals, with a 1 in the numerator all the time, p is the power that's not changing. Power 4, power 4, power 4, power 4, forever. And inside, then the what is inside this power, or the base of that power expression, is what's changing. So that's the n. So this general form, a sub n of 1 over n to the p of a sequence, where the power that's not changing has to be greater than, it has to be a number, of course, and it's the same number on every term. So the number, the power doesn't change. It has to be greater than 0. So it's just any number, any real number greater than 0. That means it could be an integer, like 4, 4, 4, 4, 4. It could be 3, 3, 3, 3, like that. Or it could be 100, 100, 100, 100, 100. It could even be a decimal. 0.2, 0.2, 0.2, as long as it's any real number that's positive. And by the way, it could even be like a pi. Pi is a real number. It could be pi, 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 like that. Okay. And the name of this sequence is called, when it has this form, it's called a p sequence. Think of it as the power is not changing in the denominator. Of course, we could move all this up, and if we move n to the 4th up, it would be n to the, if we moved n to the top, then it would be n to the negative 4. But in terms of recognizing a p sequence, quote unquote p, then you need to have it in this form, 1 over n to a power that's a positive power greater than 0. And if we bring it up on top, it would be n to the negative 4. And now, even though that's equivalent to this, well, now we don't have it in the right form. So you just have to move it back down. That's all. So just, if it happened to be up here, then just move it down. If there was like a 2 on the top, you could just take the 2, multiply 2 out in front, and then you would still have a 1 over n to the 4th, for example. Okay. Any questions so far?
No.
No, it just has to be, the numerator has to be 1, right? It can't be
Yes,
any
and
other
if
number.
it's any other number up here, say it was a 22, well then just factor the 22 out in front and write it as 1 over n to the 4th, like that.
Okay.
But it could not be like whatever, n factorial or something on the top, or the square root of n or something. Well, if it is, and you can simplify it, then that's fine. But it has to be a number on the top, okay? And the number, if it's not a 1, then just factor it out, and so that there is a 1.
Okay.
Okay. So, what is that called? A P, that general form like this, it's called a P sequence. And thus, when we're asked to add up all the terms that of a sequence that has this pattern, this P pattern, this P sequence pattern, when we're asked to add them up forever, add up the terms, it doesn't have to be starting at 1. It can't be 0 here, because if you had a 0 down here, it would be 1 divided by 0, and that would be an undefined number. So that wouldn't. So it's going to have to start at 1 or anything later. It could say starting at n equals 2 or n equals 3, but okay. And now this means to add up the terms forever, which means it's a series is what we're being asked to analyze, which again is a fancy way of saying just add what's happening to the sum of these terms when you start to add them up forever. Are they converging to a single finite sum number or not? Or does it just surpass any finite value and the sum just keeps getting bigger and bigger forever, and that means diverging to infinity? So yeah, so then if we have this form, it's called a P series that we're being asked to analyze. Thus, and now I'm going to try to make the connection with what we did up here, because this problem, 1 over n to the 4th, is a P. This sequence is a P sequence, and because it has this form of 1 over n to the P happens to be 4 in this problem, and we analyze this P sequence, or adding them up forever, the P series, by using a test after we did the first step and then realized that, hey, there's a chance that this series can converge. So further exploring, we used a test, a series test. Well, we only had 2 of them so far, geometric and integral series test. So the author wanted us to use the integral series test for 2 reasons. 1, to practice the integral series test, and 2, secondly, now so that we can make the connection that because even though this can be, and we did use the integral series test to determine the convergence or divergence of this this series up here, we determined with the integral series test that it does converge. That's what all this work was. And by the integral series test, this adding all the terms of this sequence, which we can also say thus the series does converge by the integral series test because the improper integral converged. But now we can make this connection. All P series, which would be all of this type, and someone asked if that's not a 1, you can move it out in front to make it a 1, then, which will make it a P sequence, or with the summation symbol, a P series. So all P series, 1 over n to the 4th power, 1 over n squared, 1 over n to the pi power, 1 over n to the 1/3 power, all of those P being any real number that's greater than 0, all of these P series would meet the conditions of the integral series test. And so if we were to check the continuity, positive, decreasing, they would pass every single time. And then also any formula that's of this form, which is a P series form, then would be easily integrable. Yeah, we would be able to easily integrate this because you would just move it up and use the power rule, which is exactly what we did right here. We moved up the x to the 4th, and it became x to the negative 4th, and you're always going to have just a 1 here because the number is moved out, and if there was something else with x or something, then if you couldn't reduce it, then it would not be a P series, and you wouldn't be able to compare this anyway. It would be a different problem. But anyway, this will always become an easy integral because it'll always be, we always will be able to use the power rule. And then once we integrate it, evaluate it, we will get this improper integral converging or diverging. When we did it on this one, it converged. And so all P series would meet the conditions of the integral series test and would also be easy to integrate, as I just mentioned. And thus, we would be able to determine the convergence or divergence of the improper integral, like we did up here. And therefore, once we've determined the convergence or divergence of the improper integral, then the series, which was our initial curiosity, our initial question to explore and analyze, we would know that it does the same exact thing as the improper integral. And so that's so good. But, so they decided the method, so some people, however many hundreds of years ago, I'd have to think about it. I can't remember who did it, or what group of people, but they came up with, hey, gosh, they had to say gosh too. I know, not funny, but anyway, they said, hey, all of these type can be we can use the integral series test, and it's going to be a simple integral to integrate using the power rule. So instead of us having to do that every single time we get a sequence that has this form, we can we can make a generalization that if P has to be a positive real number, and it's a simple proof, if P is one type of number that's greater than 0, then the improper integral will always converge. And if P is another type of positive number, this improper integral will always diverge. So therefore, we can use that so that in the future, every time we have one of these forms of a sequence and we're asked to analyze the series, we don't have to go and do all this work on the integral with the integral series test. I mean, we could, as we just did with this problem number 8, but it sure is a heck of a lot faster if you just take a leap to the generalization of, if P is one kind of positive number, then this improper integral will always diverge. And if it's another type of P number, it always will converge. So let's just use that. And therefore, the discovery or the proof of the next series test that we are learning was created. And that is the P series test. So, so I'm going to write down that now, and we'll see how that works out for us. So, well, I'm not going to try to write some sentence that I just described that tried to make a person understand that they found a generalization based on this P. I'm just going to write the results. So the P series test. So, well, when can we use the P series test? Well, the sequence has to be a P sequence. Yeah? So, if a sequence has the general form of A sub n, or whatever name, could be B sub n or C sub n, but our author uses A sub n virtually all the time, equals this formula right up here, 1 over n to the p power, which means this is a P sequence, which means if we're asked to add all the terms up forever and determine if they converge or not, then we're looking at a P series. So remember, with P has to be greater than, what did we say when it's written just like this? P has to be what?
Greater than 0.
Mm-hmm. Then the series from n equals 1 or n equals 2 or whichever starting n value, can't be 0 though, because to infinity, of this P sequence will well, what happens with any series? When we add up the terms of a sequence, they're either going to converge or they're going to what?
Diverge.
Diverge, okay? And when P is one kind of value, and it's going to diverge when P, which is a positive real number, is a different kind of number. That's positive. What was the value of our P on problem 8 class? What was our P value right here? It was what?
4.
A 4, huh? Yeah. And what happened to the series? It turned out that it what? Converged, diverged, did what?
Converge.
Converged. So whatever we write for this one converges when P, well, 4 better be part of this situation up here because we just proved when P is 4, it converged. So, and it turns out when P is greater than 1, then the series 1 over n to the P power will always converge. Well, what's the only other possibility then? If P has to be a positive number and P greater than 1 is already used up for the converging part, then what's left over for when it's going to diverge? When P is what? So what else is possible? If P is not greater than 1, it has to be what?
Less.
0 or negative.
It has to be less or equal to what?
0.
Your close. P has to be greater than 0. P has to be greater than 0 because that's what we have right up here. P is greater than 0. So if P is greater than 0, but, well, if it's bigger than 1, like 1.1 or 1.2 or 2 or 3 or 4, like our problem, it's going to converge. So what's the only other possibility? If it's P's not greater than 1, then what's the only other possibility? It could be less or equal to what? To 1? Can you guys hear me okay?
Yes.
Yes.
Okay. So if you think of a number line, and this is the P number line, here's 1. So if P is greater than 1, I put a parenthesis here because that means not including 1, then the series is going to converge. But P has to be greater than 0. Up here, we have that. P has to be, when it's written in this form, to be a P sequence, then it has to be, the power P has to be a real number greater than 0. So we're only looking at these values of P. So if P is greater than 1, then the series is going to converge. And what's the only thing left? Well, when P is at 1, which means equals 1 or smaller, which is all this part. So if P is any power right here that is equal, if it's equal to 1, it's going to diverge. Or if it's less than 1, it's going to diverge. But it still has to be greater than 0. Otherwise, we can't even call this a P sequence. So this is when it would diverge. Any questions there?
No.
No.
So how could have we done number 8 then if we did not wish to use the integral series test? Does this have the form of a P sequence, guys?
Yes.
Yes.
Yes. So this is a P sequence. 1 over n to the P, where what's the value of P on this problem right here? What's the value of this P?
4.
4. And since the power 4 is greater than 1, the series must, well, it either must converge or must diverge. And what did we come up, what does this P series test tell us? If you have a P sequence 1 over n to the P form, and you're asked to analyze the series, which means add up all the terms and see if they converge or diverge, then what happens if P is greater than 1? The series will what?
Converge.
Converge. And what did we get for the, what's the P value for this sequence? The P value is what? It was P equal to what?
4.
4. And 4 is greater than 1. So the series must what then?
Converge.
Converge. The series must converge by, now we did not use the integral series test. We used the result of it in theory, and we did not use the geometric series test. We used the new one, which is the P series test. And we would be done. Any questions there?
No.
No.
So what's a little more efficient, huh? If you have a P sequence, which means it's in this form, we could always use the integral series test, check the conditions, integrate it, the improper integral, evaluate the improper integral, take the limit, and see if this improper integral converges or diverges. And whatever the improper integral does, then so does the series. That's the integral series test. But instead, why not just use the power series test when it's a P sequence and just simply take 5 or 10 seconds and look at the power. If the power is greater than 1, well, then the series converges and you're done in 15 seconds. If it's between 0 and 1, including P equal to 1, well, then the series diverges. And that takes not all that analysis of the integral series test, but just the P series test is incredibly simple once we get there, and you just look at the power. Done. Okay, but I know you guys don't want to do that. I know you would rather do the integral series test instead, right?
Well, wouldn't we have to anyways? Because we have to find out the actual value of where it converges to.
Good question. So, number 8, this is 1 over n to a power, and P is equal to what?
4.
4, which means by the P series test, we know that it will what?
It will converge.
Converge. But this problem by the author told us to do what? To use the P series test or to use the integral test?
The integral.
That was pretty cruel of the author, wasn't it? Because in order to do that, then you have to evaluate the improper integral, check the conditions first if the integral series test can work, then integrate it, then find whether or not the improper integral converges or diverges, and then we get to decide about the series. So for this problem, Denise, you're absolutely right. We would have to integrate it anyway.
Mm-hmm.
There is no need for us to use the P series test because they are requiring us by WebAssign problem or the author to get this value of the improper integral. You're correct. However, after this connection has been discovered, like we just talked about for an hour almost, in the future, when you get a sequence that's a P sequence, they're not going to ask you to evaluate the improper integral on the WebAssign. They're just going to say, hey, does this series converge or diverge? And then we are going to do the first step, which is take the limit of the individual terms. 1 over infinity goes to 0, so there's a chance the sequence can converge or not. And then say, okay, I need to explore further, use one of the series tests. All I have right now is geometric, integral series test, P series test. Well, which one will be the most efficient if all they're asking us is this question on the top right here? So then what would be the most efficient?
P series.
P series. And you're like, well, they're not asking us here. You're right, because the author is trying to get us to see the connection.
Okay.
But look down here now, or in the future sections. This, by the way, I accidentally repeated the question as with number 8. So this is the same question we just did. So we already have this done. So 1 divided by 3 and converges. Yeah. So we did that already. I should have erased it. But anyway, now what about this? Number 15. They say here 1 over, 1 over, 1 over. They're not coming out and saying, well, actually they said that right here. It is a P series, but they're not. We just have to, they make us think a tiny bit and they want us to figure out, well, what is the n to what power? So we just got to figure out what power it is. And that's why they're asking you here, well, what does P equal? And then we can just, very good. I think it was, so someone said 1/4.
1/4, yes.
And therefore, you don't, Denise, they're not asking you to integrate the improper integral on this one. Yeah?
Mhm.
So, and so let's do number 15. Well, since it's so short. This right here is when, oh God, when n equals 1. Maybe I'll write it on my paper, okay? So, so let's go to 15 now. And I hope I will answer your question, Denise, more completely, okay?
Okay.
So, and this is 9.3 still, exercise 15. And they gave the problem to us in a different form. And the reason the author did that is because the P series is so darn simple to begin with that to make us think a tiny bit at least, we got to first recognize what is the power P on this P sequence. So that was just the author's way of making us do a little bit of thinking. So we're given a sequence. The author wrote it as adding up the terms forever, which means the series, but the sequence is the actual terms. A sub n, now we don't know the formula, not yet, such that and let's write down the terms to establish the pattern. N equals 1 and so forth, n equals 2. And which means the first term, the second term, if we call it A, and so forth. Now, the numbers given to us were, I'm not, you can't see it, but it was 1, all of them were 1 over. And it was 1 here only. And the author did that on purpose to try to mess with us a little bit. And then it was 2 root 3 or radical 3, radical 4. And then it wasn't root 2 though, because they have a root number here, and if you leave it empty, if you leave it blank, that means a 2, root 2, but it was a root what?
4.
4. If I can draw a 4 so that you can see it, would be nice. Well, that really means then we could erase this. And again, the author did that just to mess with us, to make us think a little tiny bit more and say, oh, you know what? Even though that was written as a 1, we can write this as a root, 4th root of 1. Because what's the 4th root of 1 still?
1.
1. And having trouble writing the root numbers there. So then all the way out here would be forever, well, not forever, but the nth term. And this would be then the fourth root of n would be the general term for any nth term. So therefore, this formula right here would be 1 over the fourth root of n, or a sub n equals 1 over, and this is where at least one of you noticed what the power is, because how can we rewrite this from radical form to just a power form? We would write the 1 goes in the numerator, the denominator of this fractional exponent, and the root goes in the other position. Where does the root always go? In the numerator? I mean, it's in the whole denominator, but of the bottom, in this fractional exponent, where does the root go? In the little numerator here or the denominator here?
The denominator.
The denominator. That's like this. The square root of x is equal to x to the 1 is in all these invisible power is 1. The invisible root number is 2, and you get x to the 1/2. So yeah. So if you had this 3 to the, let's say that's a 4 and that's a 2, well then this would be 3 to the 2/3, like that. But we have, and if it was 1 over, well then we would write it as 1 over 3 to the 2, oh, I think I wrote the wrong number here, sorry. And this would be 3 to the 2/3 power. So I hope that helps you. So this can be written as 1 on the top still, and to the 1/4 power. Is that okay?
Mm-hmm.
And then we're supposed to say, yay, this is a p sequence. It has the form 1 over n to the p power. So we say, oh, this is a p sequence with p equal to what, Denise, then?
1/4.
Mhm. Therefore, by the p-series test, with p equal to 1/4, which is less than 1. Well, it's less than 1, but you can say less or equal to 1, or however you want to say it. It is a positive number. The series, now they didn't write the form of the series in the problem. They just wrote this plus this plus this plus this forever, which means the series. So the series from 1 to infinity of 1 over n to the 1/4 must. So what happens when the power p, it's a positive number, it's a p sequence, and it's the power is 1/4, which is, it's not greater than 1, it's less or equal to 1. Well, specifically, it's less than 1. So which part of the p-series test do we get to use here? Well, when p is any number less or equal to 1, but it still has to be a positive number, so 1/4 is like right in here somewhere on this little number line. So then we know the series, what of course, does what?
Diverge.
Diverges. Any questions here?
No.
And must diverge. Which means, and in this case, for a series, since these terms are all positive, when you add them up forever and they diverge, they must continually getting bigger and bigger. They don't get closer and closer to whatever, 18 and never pass 18 or get to 18. It just keeps getting bigger and bigger forever, which means infinity. So they must diverge to infinity. Now you don't have to write to infinity, but it should make sense. Okay?
Mm-hmm.
Any questions here?
No.
No.
Brian, you okay? Josh, you okay?
Yes.
Okay, so now let's just try one more. And so here, p was equal to 1 divided by 4, and therefore diverges. And we're correct. And Denise, again, you're right. In this particular case, even though this is a p-series, the author is asking us to do it the slower way with the integral series test, yeah?
Mm-hmm.
Yeah. So there's only 2 of those left, and this one or this one. And I don't know, how about 11? So we have, there are the terms of the sequence. And of course they have them added, which means they want us to analyze what happens when you add all these terms up of the sequence forever. Does it converge or diverge? So we write down the terms of the sequence, and the first term is when n equals 1 and it happens to be 1. I'm going to write 1 over 1 again, and then we're going to have to adjust it. So the author is going to mess with us a little bit on this first term and just write 1, and then we're supposed to see, oh, but this 1 can be changed into a, so that it looks like these other ones, so we can recognize the pattern. So I'm just writing down the terms on my notebook here. Number 11. And notice these are all cube roots. Okay, so I wrote it down. I'm going to switch to my notebook. Number 11. We have here are the terms they gave us. And this is the first term when n equals 1 or a sub 1 and so forth. Okay. So, first of all, the first step is to, well, if we stay consistent with what we have been learning as the overall structure and strategy of this problem is the limit of the individual terms of the sequence. And they didn't write a formula here. Well, we can figure out the formula, and we're going to have to, but just observationally, we could notice that all the numerators are 1. And if we put this in a calculator, these numbers here on the bottom are getting, well, I guess we could find out. So let's see. So we have 1 divided by 1. Well, that's obvious. 1 divided by and they're cube root all the time. And the next one is 4. And we get that. That's smaller than the first term. So far, so good. This one changes next to 9. That's smaller yet. So far, so good, observationally speaking. Oops. And this one was a 16. Smaller yet, and so forth. Now, that's not a formal proof that the terms are getting converging to 0, but it certainly is a legitimate observation, and this is getting smaller. Okay, so observationally, these are getting smaller and smaller, closer and closer to 0, and now we're gonna formally show it, but we really can't formally show it until we have the formula. So I'm gonna go back. And so let's see if we can come up with a pattern. I'll do the tough part. The numerator is always 1. Thank you very much. Okay. That was not funny, I know. Okay. And what about the denominator? You're like, well, that doesn't have a root, but all the rest of them do. So therefore, we know we can change this one. So just change 1 so that it's a cube root. And to be a p sequence, for the first term, there has to be a 1 in form. I mean, it has to be so that a 1 pops up here. And for n equals 2, there has to be a 2 popping up, and a 3 and a 4. And right now it's not. So we have to do a little tiny adjustment here. So we know it's going to be a cube root. There has to be an n. And then, well, if that's all, if this is it, if we're done, is this the right formula? Is this correct?
No.
Question mark. No, because if we put n equals 2 in, then we better get this up here. But if we put a 2 right here, then there's actually a 4 showing up. So then it's not just n. So something needs to be done to n. And now that's where we catch the pattern. So what do you have to do to 2, which is our n value? What are we going to have to do to it right here? Well, you might say times 2. Because 2 times n equals 2 times 2 is 4. But what about the next one? When n equals 3, what's 2 times 3? 6, but we're supposed to get a what?
9.
9.
Well, that's not right. So it's not times 2. So this is the part where we have to do a little bit of thinking, is to find the pattern. Because the p-series test itself, once you get the p value, well, then it's incredibly simple. So that's why the author is challenging us more. So what do we need to do to this n so that if you put a 2 there, you get 4. If you put a 3 there, you get 9. If you put a 4 there, you get 16, and so forth.
Square.
Square, good. So these are squaring numbers, so that's supposed to be the clue. So if we test it, if you put a 1 right here, 1 squared is 1, cube root of 1 is 1, and that's what they had to begin with, yeah? Okay, and so that'll be right. If you put a 2, 2 for n equals 2, 2 squared is 4, and we get 1 over the cube root of 4. And for 3 and 4 and so forth. So we found the correct form of this, the terms of this sequence. And we can rewrite this as a sub n equals 1 over n to a power, because we're trying to make this into, because it has 1 over, so we're trying, if possible, to make this into p-sequence form so that we can use the simpler p-series test versus some other test. Okay. And what does this become then? Of course, it's fractional power, and it's what, Josh? What are we going to put?
2/3.
2/3. Any questions here?
No.
And what form is this sequence then? It's not geometric. You can't say integral, that doesn't make sense, but we could use the integral series test here. But
P-series.
this is a p sequence, huh?
Mhm.
With the p value is 2/3. And since we have a p sequence, then, and we're being asked to find out what happens when you add up these terms of the sequence forever, starting at n equals 1 forever, then let's use the p-series test. Since p equal to 2/3 is what, of course? What are we supposed to be comparing it to if we're going to use the p-series test? If it's either, what two possibilities?
1.
So if it's greater than 1, and what's the other situation? If it's between 0 and 1?
Mhm.
But not including 0. It has to be positive. So where is 2/3? Where is 2/3 on this number line that's been broken up into two parts? The diverging values of p and the converging values of p. So where is 2/3, Brian, here? Is it greater than 1 or less than 1?
Less than 1.
Yeah. Now, obviously, 2/3 cannot be equal to 1 and less than 1 at the same time. It's just, if it's equal to 1, well, then it diverges. If p is less than 1, it diverges. As long as it's greater than 0. It has to be a positive number when you write it in this form. Any questions there?
No.
No.
So then we say, since p equals 2/3 is less than 1, or if you wanted to be formal, we could say, oh, 2/3 is less or equal to 1 and greater than 0. If that's what a person wants to write it as, then that means it fits in the diverging category. But you can also just write this, hey, it's less than 1, which means it's going to diverge. So either way, since p equals 2/3, the series Now they didn't give this to us. They could have asked us to write it down, but they don't. But if they did, we would write 1 over n to the 2/3 power, and must, are we gonna write must what?
Diverge.
Diverge. By the, or using the P-series test. And we're done. Any questions there?
No.
Okay, so good. Go back to WebAssign. And it was number 11. The p-value is 2/3. So really, this is what the author, this was where the author made us think, was to figure out how to change this into precise p-sequence form, and so that we can figure out the p-value, because once you get the p-value, then it's incredibly simple to determine if it converges or diverges. So, and this one diverged. And hopefully we are correct. And number 11, we are correct. So for this assignment, it appears that, well, I told you guys, if you wanted to wait on problems 10, 11, and 15, then do so, because of that discussion that was needed to understand the next series test on our list of 8, which is the P-series test. So now we're gonna learn one more. I was hoping to get to 9.6, but the nice thing about 9.6, I guess it's gonna have to wait till next Monday. And it's a very short, there are 2 tests actually, and both are short, and it's really just algebra. And taking a limit, I should say, but with algebra. And it's very, very quick and very short. And the next one we learn is also short, not quite as, but it's still nice. So, oh, what am I doing? So I'm gonna move to the next section. And that is, and 9.5. There must be a mistake here. There's only 8 problems here. That can't be right. No, I'm kidding. Yep, there's only 8. It's only 1 test, and it's fairly, there's not that much to practice. It's just 1. So here we go. Okay. So I'm gonna pick one here. Let me scan and think about it here for a moment. They look a little scary there. However, okay, so my brain had to be thinking about all the steps required to do these problems, and therefore then to make a decision where I want to begin to in your best interest. So, so I did that, and I want us to start with number 3. Okay, so this is section 9.5, and it's exercise number 3, and here we go. I'm gonna, oh, I better write it down. Okay, so going to my notebook. Okay, so 9.5, number 3, and here we have, this is 8n minus 1. Okay, so there's just a couple thoughts we have. Well, first of all, let's just look at the terms. So the first, this, oh, I guess I forgot to write it. Let me see. Starting at 1, okay. So this is from 1 to infinity. Okay, so at n equals 1, and forever, and these are fractional because the formula has a fraction bar. And let's see, if we put 1 in, we'll get the first term and so forth. Okay, and I'm going to purposefully, for just a moment, ignore this part. You're like, what is this teacher doing? It must be crazy. By the way, what does this part do? We talked about this a little bit, I believe, maybe not. What happens when you put a 1 right here for n? What's negative 1 to the first power, of course?
Negative 1.
Negative 1 times whatever this is. What happens when you put a 2 in? What's negative 1 squared?
1.
1 times whatever this is.
Mm-hmm.
N's are positive numbers because they represent the terms of the sequence. So if you put if you put a 2 and a 2 here, or a 3 and a 3 here, or a 4 and a 4 to get the third term, the fourth term, the fifth term, the first term, n equals 1, you're going to get positive. This is going to be a positive result. And then this positive result would be some fraction, positive fraction times this part. And this part makes it change because when you put a 1 in, negative 1 to the first power is negative 1 times this positive number. So that means this first term is going to be what? Positive or negative?
Negative.
Negative. And when you put a 2 in, negative 1 squared is positive 1. Positive 1 times a positive fraction will be what?
Positive.
Positive. When you put a 3 in, negative 1 cubed will be, what's negative 1 cubed?
Negative.
Negative 1 times this positive fraction will be a negative. So what's going to happen to these terms? They're going to be start with negative, positive, negative, positive. So they're going to do what? What's that called?
Oscillate.
Oscillate or alternate. Good. Very good. So this part makes it alternate from negative to positive. So this sequence is called an alternating sequence. So this is another type of formula that can give us terms forever that we could want to explore. And therefore, we may or may not, we will get a new series test, and we will potentially use this if we have to explore further. But there's always that first step that I've been trying to establish in our minds as the part of the overall strategy for any sequence. First, do what, guys, ladies, is to first look at the individual terms and see if they what?
Alternate?
Well, yeah, you're right. This would alternate because of this piece, but just the general idea of any sequence. And then when we're asked to add them up forever, what's always our first step besides writing the terms down? What's always, so regardless if it's this problem or another problem or whatever, what's always our first step after we write the terms down?
The limit
The limit of what?
of a sub n.
I'm sorry?
Of a sub n.
Of a sub n, good. The individual terms of the sequence. And then we're going to check and see if the terms of the individual sequence or the limit of a sub n, as you said, equals what? Converges to what?
Or a finite number.
To a, and good, to a finite number. And which is the only finite number we can get, which means we have to keep further exploring if the series converges or not. When these individual terms converge to what?
0.
0.
0. So the same thing here. If these individual terms converge to 0, well, then we have to keep exploring, don't we?
Yes.
Mhm.
Which means use a series test. What happens if these terms right here don't converge to a single, well, if they don't converge to 0, then what?
They diverge.
Then if it's a single finite number other than 0, then the terms of the sequence will converge, but when you add up the terms forever, it will what?
Diverge.
Diverge. If these individual terms diverge, well then also when you add them up forever, they will diverge. And that's that first step we always check, which is the nth term test for divergence. Yeah?
Mhm.
Is that okay?
Yes.
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 So we're going to write the first 4 terms down and then do our first step, which is to analyze the terms, individual terms of the sequence and see, and if we get 0, well, that means we keep exploring. And that means we have to use one of the series tests, which now the list is growing. Geometric was the first one, series test. The integral series test was second. The third is P-series test. And now there's going to be a 4th one, which is the alternating series test. But we always want to do the first step initially. And if we're lucky in a sense of being done quickly, if we want to call that lucky, then if these individual terms of the sequence do not converge to 0, if they converge to 0, we keep on exploring. If they don't converge to 0, we're done. Yeah, is that okay?
Mhm.
Okay.
Yes.
So let's write down the first few terms of this sequence. So we put in the 1, so we can do this mentally. We already, -1 to the 1 is -1. So we're waiting right here. -1 is waiting to whatever we get here. So if we put a 1 here, 8 times 1 is 8 minus 1, Josh, is what?
7.
5 times 1 plus 5.
6.
And -1 is this first part times 7, 6 is -7, 6. So there's our first term. And now the second term. Put a 2 in, and -1 squared, Brian, what's that going to be? -1 squared
1.
times, put a 2 here, 8 times 2 minus 1,
15.
5 times 2 plus 1,
11.
and 15 over 11 times 1 is 15 over 11, but positive. And now we have this negative, positive forever, which makes this alternating. Yeah, the sequence is an alternating sequence. Keep going. Denise, the next one, -1 cubed.
+1.
So what's -1 times -1 times -1? 3 times.
-1.
-1 times, put a 3 in, 8, 3, 8 times 3 minus 1,
23.
good. 5 times 3 plus 1,
16.
that doesn't reduce, so we write -23 over 16. And one more. Put a 4 in, Josh. What's -1 to the 4th power?
Positive.
+1. Put a 4 here. 8 times 4 minus 1.
31.
5 times 4 plus 1.
21.
Multiplied by 1 is positive 31 over 21. And this would continue forever. Alternating, but now we want to analyze the first step. The limit as n approaches infinity of the terms of the sequence and what we want to see is if these are getting smaller and smaller, closer and closer to 0. If they are, then there's a chance that the sum of these terms could converge. If these terms do not get closer and closer to 0, then we're done. And we don't need anything further, no further exploration. We say the series diverges by the nth term test for divergence. Is it okay?
Mm-hmm.
Yes.
So I'm going to put these into our calculator, and so that way we can get a better sense. Also, we could graph this. Oh, well, I'm going to show you something. So, okay. Okay, so we had the first term is -7 divided by 6. The next term was +15 by 11. The next term was negative 23 divided by 16. The next term is 31 divided by 21. So let's see what, it's only 4 terms. It alternates, we knew that. Negative, positive, negative, positive. Now I'm going to use this marker here, or stylus, and I'm just and we don't care about we only care about starting right here at n equals 1. And oh, so I better be careful here. At n equals 1, the term is negative 1.16 something. So this is negative 1.2, 1.4, 1.6, 1.8, 2.0. So negative 1.16, you know, it's something like in here, approximately. It's a negative number, and so therefore it's underneath this axis. And the next term is when n equals 2, and the second term of our sequence, and that turned out, because it's alternating, it's positive, and it's 1.36. So here's 1, 1.2, 1.4, 1.36 is right in here somewhere. The next term is negative 1.4375. So that's when n equals 3. Negative 1.4, 1.2, 1.4, and a little more. So it's like right in here somewhere. And we only have 4 written down. When n equals 4, we get 1.47 something. So here's 1.2, 1.4, 1.6 is too much. So it's like right in here somewhere. So visually, observationally, what's happening to these terms here as we go out? First term, second term, third, fourth, fifth, so forth. They're going to alternate, negative, positive, negative, positive. The next one's going to be negative at a sub 5. But what's happening here, class? Are these dots here, which represents the values of the terms, they're alternating, that's okay. But they have to be, remember, the limit of these individual terms, the first step is they have to be converging to 0 if there's any chance for the sum of the terms to converge. Well, what about these terms? They're alternating, that's okay. But they need to be alternating and getting closer and closer to 0 for us to have a chance, for not us, but for the series to have a chance to converge. And what does it look like these terms are doing right here? They are alternating, but are they getting closer to 0, or are they going further away?
Further.
Yeah, the next one might be like right here or something. And the next one might be right up here. I should think for a second. I should have been more careful. It's really like right here. And the next is like right here. And the next one is right here, and so forth. So, does it appear that they're getting closer and closer to 0 here, observationally?
No.
No. So that's, in an observational sense, no. Okay. Now, it appears visually, observationally, that the limit as n approaches infinity of the individual terms of the sequence is not, it's not converging to 0. Actually, and really that's enough. I mean, well, I'm going to show you formally as well. But in an observational sense, these terms are not getting closer and closer to 0. So we could just say in an observational sense, we're done. There's no chance then when you add these up that it could converge at all. And that would be by the nth term test for divergence. But let me show you formally what's this limit. So formally, the limit as n approaches infinity of this formula yeah, we know it's alternating. And it's alternating from negative to positive, back to negative to positive to negative to positive forever. Okay? But to what? Is it could be going like this, where these terms are alternating but getting closer and closer to 0. And that would mean that we would have to continue and explore further. What else is possible when they alternate? They don't get closer and closer to 0 alternating. That would be like this. If it was, just pretend, just pretend it was like this, and the next one was closer yet but positive. The next one was closer yet but negative. The next one was closer yet but positive, and so forth. That's when they're alternating but getting closer and closer to 0. And if that happened, we would have to explore further. What else is possible when they alternate from negative to positive like that? Another possibility is when, say the first one's negative, like it is, and then switches. If pretend they were getting closer, like they are here. Let's say they were getting closer to -2 and positive 2. Getting closer to negative 2 and positive 2. They never make it to 2 and negative 2, but they're getting closer and closer. If that was going to happen, class, then when you took the limit and you did, if you ignore this part, because that's just the part that makes it negative and positive. And if you took the limit of this only, if we got 2, then that would mean that in half of these points would be getting closer to negative 2, and the other half of these points would be getting closer to positive 2. But that's not converging. That's just they're alternating and they're getting closer to 2 on one half and negative 2 on the other half. And that's an alternating type. You remember, class, that we talked about the 3 types of diverging limit values, determinant limiting values. One is infinity only, one is negative infinity only, and another is oscillating or alternating. And so this one is an alternating sequence, and if it's alternating positive, negative, closer and closer to 0, then we explore further. If it's alternating though, but negative, positive, but getting closer and closer to say a 2 underneath, a negative 2 underneath and a positive 2 above, well then that's a diverging, the terms are diverging because of the alternating type. Or what's the other type of diverging on the on any limiting value question is, if they don't get closer and closer to 2 and negative 2, well then they could just keep going larger past 2. I'm sorry, that would have been like right here, past 2, below negative 2, and then they just keep going upward forever and downward forever. And then what? Half of these terms would be getting closer and closer to what's forever upward?
Infinity.
And the other half getting closer to what?
Negative.
Negative.
And that's still oscillating or alternating, but not to 2 and negative 2, not to 3 and negative 3 or something, but to infinity and negative infinity. And that's still diverging. And we would be done by the nth term test for divergence. Is that okay?
Mm-hmm.
Okay. And so what's happening on this one? It's alternating negative, positive, negative, positive. But we can find out not only observationally what's happening, also we can do it computationally, formally, by doing what I'm about to show you. This part makes it alternating. We already know that. Now let's find out. What is the limit of this part right here as you go out forever? And this is going to give you, if the limit is getting closer and closer to 2, if we get 2 right here, well, that would mean half of them get closer to 2, the other half get closer to negative 2. If we get infinity right here, when we ignore this, then that means half of the points are going up forever and the other half is going down forever. Or if we get 3, then half of the points are going up to 3, closer and closer, and the other half closer and closer to negative 3. If we get 0, then that means the points are alternating, but they're getting closer and closer to 0, and that's when we proceed. So how do we find it formally? We just take the limit of this part and find out, do we get 0? Do we get infinity, which is one type of diverging? Do we get a constant, 2 or 3 or 1 or 1.6 or what? So the limit as n approaches infinity of just this part, 8n plus 1, I'm sorry, minus 1 well, this was the difficult part to understand this series test, was this discussion right here. Once we get past that, then it's real simple. So what is this limit going to be? Is it going to be 0, which is converging, which means we have to further explore with a series test? Is it converging to a single finite number but not 0, like a 2 or a 3? We're still done. Then we're done. Then we know the series must diverge. Or if we get infinity, we know it must diverge. So let's find out. So what can we do when we plug infinity in? 8 times infinity, infinity minus 1 is still infinity. 5 times infinity plus 1 is still infinity. And what did we get, guys, lady? Did we get a determinant? Or is this indeterminate?
Indeterminate.
And is it unfriendly or friendly?
Friendly.
So we could do one of two things here. Use L'Hopital's rule and take the derivative of the top and the bottom. And I also want to remind you, because we're going to start doing this on the next lesson, instead of, what happens if we use L'Hopital's rule? What would we get? What's the derivative of 8n minus 1? What's the derivative of 8? Oh, you could say 8x, but what's the derivative of 8n minus 1, guys?
8.
8. What's the derivative of 5n plus 1?
5.
And is there any place to put, and is there any n in here anywhere to put infinity?
No.
So we would get 8/5, which, by the way, is the same as 1.6. And then that would tell us, oh, you know what? As we go out forever, we know this part makes it alternating negative, positive, negative, positive. But they're getting closer to negative 1.6 underneath and positive 1.6 above. So half of the terms are getting close. And by the way, right here is 1.6. And right down here is negative 1.6. And I know I have these red and light blue and orange points, but those were when we were discussing. But the original terms were these blue ones. And we had negative, positive, negative, positive, and they actually are, if we kept going, they would be, half of them would be getting closer to 1.6, but never make it. And the other half would get closer to negative 1.6 and not make it. And that's what this tells us. So then we would say, as you go out forever, this alternates closer and closer to negative 1.6 and positive 1.6. So this is not getting closer and closer to 0, is it?
No.
No.
And therefore, the limit of the individual terms of this sequence, you cannot say it's getting, you cannot even say it's getting closer to one single finite number. You can't say 1.6 because it's actually negative 1.6 and positive 1.6. So we would say the limit of the individual terms is what here? Converging, not converging to 0, and it's not even converging to a single finite number, it's converging towards 2 of them. Well, that means it's not converging. So what are we going to say right here? It is what? Converging or diverging? Is it converging to 0? Another single finite number, or is it diverging?
Diverging.
Diverging. What type of diverging is it? Not to infinity or negative infinity. Not even half of them to positive infinity, the other half to negative infinity, but alternating to negative 1.6 and positive 1.6. But nonetheless, it's diverging. It's not equal to 0, and therefore, I know this took a while, therefore the series, and therefore when you start to add up these numbers, and it should make sense, I hope, you start to add these up, there's no way when you add them up they can converge to a single sum. So the series diverges when the sequence, the individual terms of the sequence is not equal to 0, and this one is not, and it's diverging, then the series diverges by the nth term test, which is that first step that we always are supposed to check by the nth term test for divergence. And we do not have to go any further and use any one of the 8 series tests, because we never made it past the first step. And because it was the first one, it just took a while for us to talk about the possibilities when it's alternating. So let's go back to WebAssign. Oh, and we are on this one. And the author was kind of trying to help us out here a little bit. What happened when we took the limit without the alternating part? They're not being very clear here on what's going on. That's what I tried to do over here. But what is the, first of all, the series diverges. And what happened, what led us to that? We took the limit, the first step, the limit of the individual terms without the alternating part, and we got 8/5, which then means, or 1.6, and that means because it's alternating, the terms are going, half of them are going to 1.6, the other half are going to negative 1.6, which means the terms of the sequence are not getting closer to 0, and we're done by the nth term test for divergence. And so here they want us to put either 1.6 or 8/5, either one, and we're done. And we are correct. Now I know that was a lot right there. I feel for you guys. It is a lot of work, but it's calculus too. I don't know what else to say. So now we look again. Well, there's only 8 questions, and we have most of the idea done, except for what happens if we take the limit and it does alternate, but get closer and closer to 0. Well, then we have to explore further, but that further exploration is a short test. It doesn't take much. So we're almost there, is what I'm trying to say. Okay, so let's see here. How about number 4? So number 4, let's see here. So let me write it down, and I'll go to my notebook. The alternating piece, the -1, not to the n this time, but n plus 1. That still means that's the alternating piece. It's simply going to be the first term won't be negative this time, it'll be positive, and then alternate. Okay, so, and I've written the problem down, and here we go. Okay, and notice the author writes this part. That's that first step that we're always supposed to check. That first step. And so, which of the alternating possibilities is it going to be? If the terms alternate but get closer and closer to 0, well, then we have to further explore. If they alternate but don't get closer and closer to 0, well, then we're done. Because if they don't get closer and closer to 0, then they might get closer to 1.6 and the other half of them negative 1.6, but we're still done. Because that means the terms don't, individual terms don't converge, they diverge. If half of the terms go to infinity and the other half go down underneath to negative infinity, we're done. Because the individual terms are not converging towards 0. So let's see. What's happening to these individual terms? Well, we could write the terms out. So let's do that. And remember, and let's do this faster this time because it's taking a long time. If we put a 1 in, 1 plus 1 is 2. -1 squared is positive 1. That means the first term, it's going to be a positive, and then times whatever is inside this part, which is 1 over 1 squared is 1 plus 6 is 7. 1 times 1/7 is 1/7. There's our first term. So if we were to make a little informal sketch, the first term, let's say that's 1 up here, -1 below. The first term is 1/7. So it's a little bit above 0. About the next term. When n equals 2, 2 plus 1 is 3. -1 cubed is -1 times, put a 2 here, 2 is 2. 2 squared is 4. 4 plus 6 is 10. -1 is the alternating, it's negative this time. And 2/10 reduces to -1/5. So this is a -1/5. -1/5 -1/5 is actually a little further away from 0 than this one was. So right now it's kind of going the wrong way. It's supposed to get, we want it to get, if it's going to converge towards 0, then this is supposed to be closer. So let's see what happens. But remember, it doesn't have to happen in the first couple terms, as long as eventually they all get closer to 0 is what we're interested in. So let's try n equals 3. Put a 3 in. 3 plus 1 is 4. -1 to the 4th power is +1. Put a 3 in this part. It's 3 over 3 squared 3 squared is 9, and 9 plus 6 is 15. And we get 1 times 3/15 is the same as 1/5. So here it went back to positive, and notice on 3, it's the same distance away as the previous one was negative 1/5, but it's positive. So that's kind of like a tie. This one's below 1/5, this one's above 1/5. Now what happens after that? So let's go one more here. Put a 4 in. 4 plus 1 is 5. Negative 1 to the 5th power is negative 1. Put a 4 here, it's 4. 4 squared is 16. 16 plus 6 is 22. And we get negative times positive is negative. But 4 over 22 reduces to negative 2 over 11. And that is negative, but it's getting closer. If we spent a few more moments, we would notice that they continue to alternate, but they're going to get close. I mean, the next one's going to have to be positive. And if you put positive 5, it's 5 over 5 squared is 25 plus 6 is 31. 5 divided by 31 sorry, where am I? So here, so we just had, we had 1/5 and negative 1, we had negative 1/5, which is 0.2. We had, well, it was negative, and then positive 1/5. And then we had negative 4 over 22, which was 2/11, and that's that. It's getting smaller. The next one was positive 5 over 31, and that's smaller yet. So what I'm trying to say is from now on, even though the first couple terms did not get smaller and closer to 0, but after those first 2, yeah, this one and then these 2, there was like a hiccup here, and this one got further away than that one, and this was a tie. But then after that, forever now onward, they will keep alternating, but get closer and closer to 0. How can we, which means we're going to have to continue in our exploration. How can we show that formally? That, so informally, we know the limit as n approaches infinity of the terms of the sequence does converge to 0. Informally. Any questions there?
No.
Okay, so stay strong here, guys, okay? Then formally, all we do is take the limit as n approaches infinity. This is just the alternating part, so just do this. N over n squared plus 6. And if we plug infinity in, we get infinity over infinity, which means we could use L'Hopital's rule. Or I was going to show you last problem that you can do it another way, which we're going to have to start learning. So let me show you here. And I've already told you this. And I remember Denise asked me a question about it. You divide by the highest exponent in the denominator. So we have n to the first, but that's in the numerator. N squared is all we have in the denominator. So we're going to divide. So one other way to find this limit, because we got a friendly indeterminate, is to divide every term by n squared. So we have n squared plus 6. We have n, and divide by every term by n squared. Yes, we could have used L'Hopital's rule, and it would have been pretty quick here. But there's going to be other situations, and not this one, where you'd have to keep taking using L'Hopital's over and over and over again, and then so doing it this way ends up being faster. And then there's some other reasons why we will do it. We'll have to do this kind of logic. And it'll be when we're not doing, well, let me just leave it at that. So, so what are we doing right now? Formally showing that these terms, even though they're alternating, are going to get closer and closer to 0. So, Denise, can you help us out here? What's n over n squared reduced down to?
1 over n.
Mm-hmm. And on the bottom, what's n squared over n squared?
1.
And 6 over n squared, does that reduce or no?
No,
No.
you just leave it.
Mm-hmm. Now take the limit, and we will not get a friendly indeterminate anymore. We're going to get a determinant. And determinant means a single finite number or diverges, which means infinity only, negative infinity only, or an oscillation type. So what happens here then, Denise? 1 over a larger and larger number gets closer and closer to what?
To 0.
1 is 1. 6 over infinity squared is infinity. 6 over a larger and larger number also gets closer and closer to what?
0.
And so we get 0 over 1. And what's 0 divided by 1, of course? It's what?
0.
0. And formally, we just showed what we did over here informally. These terms, yes, we ignored this right here formally, but we keep it in our head that this means it's alternating from positive to negative to positive to negative. But when we took the limit of this part, which gives us the numerical values, not the negative and positiveness part, but these terms are getting closer and closer to 0. And so even though it's alternating, but they're getting closer and closer to 0 in an alternating sense, which is still converging to 0. Any questions on that part?
No.
No.
So what happens when we do the first step and we get the individual terms are getting close, converging towards 0, what does that tell us then about the sum of these terms forever? What does that tell us?
It may converge.
It may converge or it may not. Very good. And we need a further test, don't we?
Yes.
And what test do we have? We have geometric. If you were to divide this divided by this and this divided by this and so forth, you would not get a common ratio. It's not geometric. Integral series test was the second test we learned. Well, to use the integral series test, Denise, what was the 3 conditions that have to be met? I'm sorry?
It has to be positive,
Positive.
continuous, and decreasing.
Good. And what about these terms right here? Are they all positive, Denise?
No.
So that means the integral series test cannot be used. It already fell apart when we got to the positive part. Is that okay?
Yeah.
Josh, is that okay?
Yes.
So the integral series test is out. P series. If it's a P series, well, then we could use the P series test. But by the way, you might remember if the P series, we could have always used the integral series test. So if you can't use the integral series test, you're not going to be able to use the P series test either. But anyway, this is not of the form 1 over n to the same power, where this keeps changing. Yeah. If it was just 1 over n squared, that would be P series. Oh, you can't see my writing. If it was just 1 over n squared, then that would be a P series. But it's not. You have the plus 6 here, that destroys it, and you also have the n up here, that destroys it. Yeah. Plus, on top of all that, it's alternating. That destroys it. So there's lots of ways this gets destroyed, and you cannot use the P series test. Is that okay?
Yes.
And so what's the next test we have? And that's the alternating series test. And it's very simple, not quite as simple as the P series test, but still simple. So it just took us a long time to get past the first step because there was a lot to talk about on the first step. Do the individual terms of the sequence, do they converge to 0 or not? If they don't, we're done by the nth term test for divergence. If they do get closer and closer to 0, even though it's alternatingly so, then we have to explore further. And geometric, no. Integral series test, no. P series test, no. Alternating series test, yes, we're gonna try it. So let's try the alternating series test. So there are, what is the alternating series test? Well, first of all, it has to be alternating, which it is. If this, so, I mean, I'm not going to write it down, you know, the condition that it has to be alternating because it kind of makes sense because that's why it's called alternating. So, of course, you can't use the alternating series test if it doesn't alternate from negative, positive, negative, positive, negative, positive, or instead positive, negative, positive, negative. It has to alternate. Aside from that, if these two conditions are met, then the alternating series we're almost there. The alternating series must converge. So what are the two conditions? So the two conditions, 1, 2. One of them we already did. One of the two we already did, that's good news, in the first step. And that was when we took the limit of the individual terms of the sequence, ignoring this part, because that was just the alternating part, and we had to get what? Closer and closer to what?
0.
0. Well, that's one of the two conditions. The limit as n approaches infinity of the individual terms of the sequence, ignoring the alternating part, which another way of saying ignoring the alternating part is just to, the absolute value of that would just take away the negatives. So I don't know, this could confuse you, or you can just say ignoring the alternating piece, or expression, which is this -1 to the n, or -1 to the n plus 1. You could either say, take the absolute value of this whole thing, which then just means ignoring that. Or you can just say ignoring that. Whichever way you want to say it, it does the same thing. And this limit, ignoring the alternating piece, has to equal 0. It has to equal 0. And we would have already have done that. Because what happens if we don't get 0? Well, then we're done. And we never even will need to get to the alternating series test. Because then we'll be done by the nth term test for divergence. Does that make sense, guys?
Yeah.
Okay. What's the second step then, which is really the only new thing you have to do, is these terms, let me say it in words, these terms, when you take away the negative and positiveness of it, these terms have to be getting smaller and smaller and smaller without, by ignoring the negative and positiveness of it, the terms have to be getting smaller and smaller, which means maybe it doesn't happen on the first couple terms, and it didn't here. 1/5, if you take the absolute, if you ignore the negative, 1/5 is not smaller than 1/7. Yeah, 1/5 is not smaller than 1/5. It's equal to 1/5. That's okay, by the way. But what eventually the terms have to either, they have to be getting smaller and smaller and smaller. So how can you write? I'm going to write it in words. Ignoring the alternating part, the -1, +1 part, ignoring this piece again. Each subsequent term in the sequence must equal, equal or be smaller forever. It may not happen in the first couple of terms, but once you get past, and in this course, they might do it to us like this. In the first couple, the ignoring the negative, 1/5 is not smaller than 1/7. But after you get past this first term, now these are equal, and after these two being equal, they do, remember we did it over here, ignoring the negative, the next term was 2/11, the next term was 5/31, and they were getting smaller. So how do you write this formally? How do you write this in mathematical notation instead of in words? You just say the next term in the sequence A, the n plus first is another way of saying the next term has to be less or equal to the one right before it, which in general we say A sub n. For all n, and this is not true when I write this, but it's really not for all n greater or equal to 1, but eventually. Because eventually, because it doesn't work on this one. This, ignoring the negative, is not smaller than this one, but eventually it has to happen. But how will authors write it? Because it's kind of hard to write it unless you say a bunch of words. They say for all n greater or equal to 1, and then they'll write in the bottom of the page, they'll say, oh, as long as it works eventually, and maybe not, if it doesn't work on the first few terms, that's okay. Okay, so what we have to do then is we did the first step. We took the limit of the individual terms, ignoring the alternating part, and we did get 0, which means these terms, even though they're alternating, they're getting closer and closer to 0. That means we need to explore further, because this sequence, the sum of these terms of the sequence could still converge. We don't know yet. So we explore further, and we're using the alternating series test. And if these two conditions are met, then the series must converge. What's the first condition? Is the first step that we already had done. What's the second step? Is to look informally and just check, is the subsequent terms smaller or equal to the one before it eventually? And what I'm going to ask us as a class to do is to just look at it informally, this second part. They couldn't, if it was a theory class or someone really wanted to be difficult, they could make us prove it. And in some cases, it's pretty simple, but in other cases, it's really nasty. So they don't typically want us to do that in calculus too. So, so informally, we are on step 2. And if we can show, and all we're going to do is do this. Write the first few terms of the sequence, which we already have, ignoring the negative and the negativeness, just the positive values. So, first term was 1/7. Second term, 1/5, but I know it's negative there, but we're ignoring the negative. The next term was positive 1/5. The next term after that was negative, but we ignore that, 2/11. And the next term is 5/31. So ignoring the negative, the alternating part, starting here, this one, no, it didn't work. This right here is not smaller than this term. But after the first term, then the subsequent terms are either equal, the first two are equal, but after that, this term is less than this one. I showed you on the calculator. 2/11 is smaller than 1/5. 5/31 is smaller than 2/11, and so forth. So informally, it is true, the The subsequent term is less or equal. Well, I'm not going to write all that down in words again. Informally, a sub n plus 1 is less or equal to a sub n starting at not n equals 1. When did it start to be less or equal? Well, starting right here. And what term was this? When n equals what?
1.
So this is when n equals 1. And this is when n equals what?
2.
2. When we have it right up here, huh? Yeah, starting right here, these terms, this was not, if you take away the negative, this is not smaller than this one. But if you ignore the first term, which we can, then from then on, they either are equal, these two are equal, and that's okay. And then after that, they're all smaller. So that's okay. So starting at n equals 2. Therefore, the two conditions have been met, and I ran out of space. Therefore, by the alternating series test, the series now we didn't have to write all this. We could just say the series we began with, as I'm just rewriting what was over here. The series, this series must converge. Any question? Go ahead.
It started converging at n equals 2.
What could you, I don't hear you very well, Denise.
Hold on. Did the series start converging at n equals 2?
Okay, good question. So this condition, the second condition is met starting at n equals 2.
Oh, okay.
But that doesn't mean, but so as long as the second condition is true, starting somewhere on this sequence, and if it starts with the first term, great. But if it starts on the second term, that's okay too, or even if it was the fourth term, or even anywhere. But as long as eventually the terms are less or equal to the one right before it, well then the second condition passes. But that does not mean you now have to say, you know what, I don't get to count the first term when I start to add up. The important question here is when you start to add all these terms up, do they converge to a single finite sum or not? Well, even though this was true down here for starting with n equals 2, when you come back up here to look at the whole series, you still say, if you add up all the terms forever, then they must converge. This sum must converge to a single finite number. You don't say starting at n equals 2. You just say starting from the beginning. And by the way, Denise, if it helps you, if you said, okay, what if I want to say at n equals 2? If all these terms starting at n equals 2 converges to something, let's just pretend. If you start adding all these terms up forever, give me a number, just pretend. It converges closer and closer to what? Just give me something.
3.
3. Okay. Well now, if you add the 1/7, well now, instead of saying closer and closer to 3, you might say closer and closer to 3 and 1/7. It's kind of like that, but
Okay.
so, but to answer your question, you don't say converges closer and closer starting, only starting at n equals 2.
That only pertains to this question, correct?
What do you mean by that?
The starting at n equals 2?
It starts at n equals 1.
So this n equals 2 part is not the part that we now have to adjust our answer and say the series, all these terms will add up closer and closer to a number as you go out further and further, but ignoring the first term. You don't, that not only do you not have to say that, it's not true. Yeah. It is true to say that these terms will converge, the sum of these terms will converge to a number starting at n equals 2, but that's not what we are interested in. We are interested in starting at 1. And so even though this is true, it converges towards something, but so will if you start at the first term. And I'm trying to not confuse you, but this second condition is saying this. If the second condition is true starting at the first term or starting at the second term or the fifth term, as long as eventually these terms are all going to be, each term will either be, the next term will either be equal to the one before it or smaller, no matter where it begins happening, as long as it happens, then the entire sum starting with n equals 1 will converge. It doesn't mean, oh, you know what? Because this one down here eventually started at n equals 5 or something, the fifth term, then, or say n equals whatever, the fourth term, then only the fourth term onward will converge. That's not what this is saying. It's saying that as long as these terms eventually become smaller or equal to the one in front of it, then these two conditions are met, and therefore the whole series, starting with the first term, will converge towards a single sum. Does that make sense? Does that help?
Yes, so the second condition took effect at n equals 2.
Say it again. Say it again.
The second effect, the second condition,
Yeah.
took effect at n equals 2. Doesn't necessarily mean that n equals 1 was out of the sequence.
Correct. Mhm.
Okay.
As long as the second condition is met eventually, whether starting with the first term or starting with the second term that happened in this problem, or even if it was another problem starting and it started happening on the third term, the second condition is met eventually, then when you go back up to the sum of all the terms, you don't have to now make an adjustment and say, oh, starting with the third term. It's the whole thing still will converge because the two steps down here were met, even though if it doesn't happen with the first term, that's okay.
Okay.
I'm trying to make it sound right, but I hope I'm accomplishing that. Josh, are you okay with that?
I think it's starting to become clear.
So, Josh, let me put it this way. This condition down here, if the terms right here, yeah, if they don't start to become smaller, the next term has to be smaller or equal to the one right before it. You know what I mean by that, right? Is that part okay?
Yes.
This second step does not say it has to happen with the very beginning of this sequence. It just has to happen eventually. So even if it took us 7 or 8 terms, and okay, now we're at the 8th term, pretend. And after the 8th, starting with the 8th term, the next term is either equal to the one right before it or it's smaller. The one after that, it's either equal to the term right before it or it's smaller. As long as that happens, then from then on, starting with the 8th term, let's say, then this test is saying the original sequence of terms starting with the first one, not with the eighth one, because that's what it took down here. But if this eventually happens, then up here, when you do start to add them up forever, you do say starting with the first term. And all of these terms, when you add them up, will converge to a single finite number.
So long as the next term is equal or less than the previous one, right?
And it doesn't mean it has to happen at the beginning. Yeah, you can have a few bumps in the road, so to speak, before each next term becomes less or equal to the one before. It doesn't matter on the first few.
Okay.
And the reason for that is, Josh, and it's a very natural confusion point, because think about it. Say it starts with the eighth term. Pretend somewhere over here is the eighth term. I'm not looking at the graph. I'm just saying, pretend somewhere out here is the eighth term, okay? And I just picked the eighth term, okay?
Okay.
And starting with the eighth term, the ones before it, it kept some strange behavior was going on like this. The first term was actually smaller than the second term. And that's not, it's not supposed to be that way. And then maybe the fourth and the fifth term, maybe the fourth term was bigger than the fifth term. I'm sorry, I said that wrong. The fifth term was bigger than the fourth term. Well, that's not what we want. We want the fifth term to be smaller than the fourth term, right?
Yes.
And let's say, you know what? But for some strange reason, the pattern of this formula makes it so that the fifth term was actually bigger than the fourth term. And the third term was bigger than the second term. And the second term was bigger than the first term. But as soon as you get out to 8, for some reason, based on the formula is what the reason is, but from the 8th term on, the 9th term is smaller than the 8th term, or it's equal. And the 10th term is smaller than the 9th term, or they're equal. And forever onward. Well, then that's all it takes. Then you can say that because the second condition has been met, it didn't get met at the beginning, but it is met eventually. And in this case, I just made it up, starting with the 8th term. Then, as long as this happens eventually, then when you start to add all these up forever and ever, they will converge. And if you're like, I just can't see that, well, then think of it like this, but I don't know if it makes it worse or better. Even if you said to yourself, well, okay, it should make sense that the 8th term plus the 9th term plus the 10th term plus the 11th forever and ever converge towards some of those terms are getting closer and closer to something, yeah, to some number. And pretend it's 3. Well, then if you add these first 7 terms that it wasn't behaving properly, if you add these first 7, you're going to get some answer. And then if you just add that to the converging sum, you'll get a new answer, but it's still converging. And I don't know if that made it worse or better, but all I can say is, I hope you can, if it didn't make complete sense, if at least you say, well, I'm just going to have to kind of believe what they're telling me here. And that is, even if the first couple terms, yeah, like this term is actually bigger than this one. But that's okay as long as eventually, and it does, right? Starting with this term now, this term is right after it. It's not smaller than the one before it, but it is equal. And equals okay.
Got it.
And as long as the next term is either equal to the one right before it or smaller, and this one's smaller, that's okay. That means we're good. As long as that happens continually now, we're good. So I don't know what else to say except to leave it at that. Okay?
Okay.
So I know you guys are probably freaking out. So we go back to WebAssign. And which one did we just do? We just did this one, right? Number 4. And we know that it converged. And by the alternating series test, and what was the first step? The first step is when you take the limit of the individual terms, ignoring, well, you can kind of ignore, not ignore, but the terms, if they're getting closer and closer to 0 in an alternating sense, which has, because this is alternating, then that's fine. And to do that formally, remember we took the limit on the first, well, here's the first step, but we actually did it to begin with right here. We took the limit formally of the terms of the sequence, and we already know they're alternating. So that's why we ignore that -1 to the n plus 1 when you take the limit, and we did get 0, which means these individual terms, they are getting closer and closer to 0, but in an alternating sense. So in WebAssign, the author is asking, hey, what happened when you did that first step and you took the limit as n approaches infinity of the individual terms of the sequence? What did you get when you ignored the negative part? We got, and what did we get?
0.
0. So, and that tells us then the terms are alternating, but getting smaller and smaller, closer and closer to 0. And that's the first step, the first condition. And then we check the second condition, which we just sort of had a long discussion on about the next, each subsequent term needs to be less or equal to the one right before it. And if it doesn't happen starting with the first term or the second term, it has to happen eventually. And that did happen. So both conditions were met, and therefore the series converges. And we check. Okay. So, and as summarizing, there's 8 questions. These first 2 should be nice, so to speak. The -1 to the n plus 1 is the alternating part, right? Okay, so everybody take a deep breath, and we're almost there. And I had my drink of water. And if we ignore the -1 to the n plus first term, then all we're looking at is 1 over n plus 5. And if we do the first step, which is to take the limit as n approaches infinity, what is 1 over infinity plus 5 is infinity? What's 1 over a larger and larger number? It gets closer to 0. You're like, well, I ignored the negative part. We ignored the alternating part. Well, all that means is these points are going to be alternating above and below, positive and negative, but they're getting closer and closer to 0.
Okay.
And that means then when we add up these terms, there's a chance that the sum will be converging to some finite number. Does that make sense?
Yes.
Josh, you hanging in there?
Yes.
Barely? You're like falling off your chair? Yeah? Ready to kill your... I better not say that word. You just hate your teacher so badly, you can't even stand to think of that person, right? I know. I've been there. Okay. So because the individual terms are getting closer and closer to zero, even though in an alternating fashion, it still means that we have to proceed. There is a chance for the sum of those terms to converge. They may not, but we have to explore. What can we use? Any of the new tests, no, any of the series tests that we've studied if they apply. 1 over n plus 5 is not geometric. You cannot use the integral series test because this is alternating, which means some of this is negative, and one of the 3 conditions on the integral series test is it has to be always positive, not to mention continuous and decreasing. And so those conditions are not met, and we cannot use the integral series test. This is also not a p-series sequence for a couple of reasons. The 1 over n would be, but the plus 5 destroys it. And the alternating part destroys it. So p-series, no, it's not. It's not a p-sequence. So you cannot use the p-series test. What's the only one we have extra now? The alternating series test. This is alternating. Well, that means we can use the alternating series test. And what does the alternating series test only do? It only tells us if this alternating series converges or not. And it will converge if the 2 conditions are met. What's the first condition? The limit is the first step. The limit of the individual terms of the sequence converge to 0. And we do know they do. These terms, even though they're alternating, do get closer and closer to 0. Is that okay?
Yeah.
What's the second condition? This actually becomes an easy test. It just takes forever to try to make sense of it. At least that's maybe my fault for not, I don't know. That's my biggest difficulty is how much to say, how often to repeat myself to give people a fair chance, you know? Anyway, is the next, if you look at all the terms forever, is the subsequent term less or equal? It's hardly ever going to be equal. It's almost always going to be less. But you have to write equals because that's a possibility, which can also complicate in our minds that equal part. But anyway, for all, either for all the terms, which means starting at 1, or eventually. And eventually is kind of a sloppy way of saying, or informal way of saying, if it doesn't happen starting at n equals 1, then it might, as long as it starts somewhere later. And the formal way is to say, or for n greater or equal to some integer which is greater than 1. That kind of confuses people. So if it doesn't happen starting at 1, then if it starts at 2, well, then that's okay. And 2 is greater than 1. So if it doesn't happen until starting with the 3rd term, that's okay too. And if these 2 conditions are met, well, then the series converges. So all you have to do now is write down a couple, and this is ignoring ignoring the negativeness, ignoring the -1 to the nth power, or n plus first power in this case. And what is the first term and the second term? And so this is what we have to do. So informally on our paper, we would make an observation and write it down. Informally, at n equals 1, at n equals 2, at n equals 3, and so forth. If you plug 1 in, ignore the -1 to the n plus 1. That just makes this negative or positive, the terms. So if we just look at this part, the n plus 5 on the bottom and a 1 on the top, if we just look at this part and start writing the terms down, Josh, what's going to happen when n equals 1? We're going to get 1 over
6.
And on when n equals 2, we're going to get 1 over
7.
and 1 over
8.
forever. Now, it does not have to be starting with the first term. If it does, great. Is 1/7 smaller than 1/7 is not equal to 1/6, but that would be okay if it was equal. But it either has to be equal to the one in front of it, or it has to be smaller than the one in front of it. And 1/7, if we put it in our calculator, is smaller than 1/6. If you have 1/7 of a pizza and compared to 1/6, well, 1/7 is smaller, isn't it?
Yeah.
Is that okay, guys?
Yes.
And isn't it 1/8 also smaller than 1/7?
Yes.
And 1/9? It's not equal, but if it was equal, it's okay. But it is also smaller than the one right in front of it, 1/8. So when this is true, informally, starting where? At what term this time? Was it starting now at the second term, n equals 2, like the last problem, or starting right off the bat?
Right off the bat.
Right off the bat. And then what that right off the bat means, at n equals what?
1.
1. Is that okay?
Yes.
Therefore, the series, well, let me just write it over here. Therefore, this series does what?
Converge.
Converges by what test?
Alternating series test.
Mm-hmm.
I have a question about the alternating series test.
Uh-huh.
You had mentioned that we could run into like a hiccup. How do we know if we have a hiccup or if we found, I guess, like what we're looking for, where it's a sub n plus 1 is greater or equal?
That is an awesome question, and that's a very loaded question, because not in this class, but in other classes, they do. I mean, they even stated in this class, but they just don't make us do it, because that would be cruel. Because there's actually sequences or terms where you go out, this term right here, for example, is not smaller than the one in front of it. And that continues to happen. Say, there's some possibilities where it might take all the way out to 1,000 terms or 500 terms, or 200 terms, or 237 terms. And then after that, they start to get smaller and smaller, or less or equal forever. And you're like, you just said the hiccup. Well, that's a pretty long, serious hiccup, isn't it?
Mm-hmm.
And there would be no way we would be expected, and I don't say it disrespectfully, it's just not it's not the course where that kind of thing is gonna show itself. But there are those possibilities. So, and I've tried to say this a couple of times now, that if they do give us these hiccups, so to speak, it's only gonna happen in the first. I mean, I don't think I've ever seen an author in a calculus 2 make this happen anything after the first 4 terms. I mean, they don't do that to us, because otherwise you'll always wonder, won't you?
Yeah.
And then you would never feel very comfortable, because you're like, okay, I just wrote 4 terms and it starts okay. Like the last one, we only went to 4, and we're like, well, I don't really know what's going on after that. Very well. Informally, we kind of see it, but not formally. So to answer your question, which is a good question, very good question, is to tell you there are cases when that could happen, but they're not going to do that to us at this calculus 2 level. So even though that may not give you complete peace of mind, but I hope you can believe that it's enough for to say, if you get to the 4th term and how do I say it? If it starts to be smaller or equal by the 4th term, then don't worry anymore. Okay?
Got it.
Okay? And you're like, oh, well, is it mathematically possible that it could happen later? Yes, but they're not going to do it to us here. Okay?
Okay.
Is that enough to give you peace of mind, I hope?
Yes, for calculus 2, yes.
Okay. Oh, so what are we going to say? Oh, we already wrote it. Converges. So here we're going to put converges. And what did this first step? Well, it had to be what?
0?
0. Yeah. Mm-hmm. Number 2 is going to turn out, it should be simple, should be relatively nice for us to do. And that takes us to 5. That also is very reasonable for you all to do. The same thing is going to happen. You can see, if you ignore this, alternating part, 1 over n to the 1/6 power. By the way, n to the 1/6 power would be a power, would be a p-series if there wasn't this -1 to the n. But that destroys it. So this is a p-series, but this is not. Okay?
Couldn't we just factor out the alternating expression?
You can only factor out a multiplied constant if it's the same constant, and that's why it's called constant, because it can't be different things. So if you say factor it out, well, then you're saying, okay, I'm going to factor out -1 on some of them and +1 on the other ones. Well, that's not factoring anymore, because when you factor out, it has to be a single number you factor out.
Okay.
Does that make sense?
Yes.
It's not. Does that mean every one of these terms has a -1 and you can take the -1 out and write it in here? Is every single term going to be negative?
No,
Is that what this means right here? That every term is going to be negative, or it's going to alternate?
it's going to alternate.
So you can't just say factor out -1. And you cannot say factor out -1 to the nth power, because that's not a constant. Because n changes, and when n changes, 1, 2, 3, 4, 5, then that means in some cases this will be -1, in some cases it'll be 1, and therefore that's not a legitimate factoring out. Did I answer your question?
Yes.
What will be the limit of this? So we know the terms are going to be alternating. But what about the numbers? Are they getting like, are they going like closer and closer to 1.6 and negative 1.6? Or are they going larger and larger to infinity, half of them, and the other half to negative infinity? That's not converging towards zero. Or is it alternating but getting closer and closer to zero? You know, like here's the x-axis or whatever. Okay. So what happens when you look at 1 over infinity to the sixth root of infinity is still infinity, and what's 1 over a larger and larger number again?
0.
That means there's a chance that this series could converge, huh?
Yes.
And now that means we have to explore further. And when we explore further, we have to use one of those 8 tests, series tests. But is this geometric?
No.
You cannot use the integral series test because this function here is not positive all the time. It's not continuous, and it's not decreasing because it's alternating.
Mm-hmm.
So the integral series test is out. P series, it's not, this would be a P series, yes. But this part makes it not a P series, the alternating part. So P series test is out. What's the only test left? Alternating series test, which makes sense because we should use it because this is an alternating series test. And the 2 conditions are, this is one of them, and this is already a pass, yes. And the next one is you do that informal check. Is the subsequent term smaller than the term right before it, or equal? For all n, starting either at 1 or allowing hiccups, Josh. Yeah? But if there's going to be a hiccup, they're not going to give it to you. Well, I mean, I can't say 100%, but I'm like 99.999%. They're not going to do it anything. If it'll only happen in like in the first 2 or 3, maybe 4 terms or something. Yeah, I've never seen it in a book, calculus book, where it happened anything past, and unless it was some exploration problem that was, you know, that most places won't assign unless you're doing something extra. Yeah, does that make sense?
Yes.
Okay, so then all you're going to do is write down the terms here, ignoring the negative part, and see that it actually will turn out that it's going to start to get smaller and smaller even at the beginning term, even starting at the first term. Okay? Does that make sense? I mean, if you have to show it, but I'm just telling you. Does that make sense?
Yes.
Yes.
And so this will be a check after you show it here, and then you'll say it's correct or true. This is correct or true. Well, for n greater or equal to 1. With these informal first 4 or 5 terms written down, and therefore this will what? These 2 will be a check, conditions will be met, and therefore the series will what?
Converge.
Converge. And this will be a 0, huh?
Yeah.
Any questions there?
No.
Okay, last one, and it'll be quick, and I mean really quick. This one looks scary. So does this one. Well, there's only 8. So leave you with this one. This one looks scary, but you can put this together. Well, I don't want to tell you more. You figure it out. But I do want to show you one of these two. Okay. And let's just do 6. If you don't get 7, you can always ask me tomorrow or Friday. No, tomorrow, yes, or Friday in office hour. You could ask me about number 7. So let's look at this one, and then we're done. So first step. And it starts to get tiring writing down n equals 1, n equals 2, and so forth, especially when we've been talking so long. So I hope you understand. So I just can't help myself. Yeah, n equals 2, and so forth. Okay. So what are these terms? So this looks scary here, different, because I don't see any -1 to the n plus 1 or something like that. So, but let's just, well, we have to analyze. I don't have, well, let me write it down here. First term, second term, and so forth. So no matter how scary or unscary, so to speak, this looks like, we still can plug it in and see what we get. So when n equals 1, let's put it in, and we're going to get sine of, all of them are going to be sine of something. So when n equals 1, 2 times 1 is 2. 2 minus 1 is 1. And we get what? 1 pi over what?
Over 2.
1 pi over 2. Do we need to write the 1 or just, or no?
No.
No. So we get pi over 2. You can put sine of pi over 2 in your calculator, or use your unit circle from trigonometry study. This is pi over 2. And the sine is y over r. R is 1. And then we get 0, 1. This point up here, without reteaching everything, sine is y over r. So r is 1. And what's y right up here at this angle, pi halves?
1.
1.
So 1 over 1 is 1. And that's what goes right here. 1. At n equals 2, we plug it in. And let's see, 2 times 2 is 4. 4 minus 1 is 3. So we get 3 pi over what?
2.
3 pi over 2. Now what does that equal to? Well, down here is 3 pi over 2. Or you can put it in your calculator. This point is 0, -1. X comma y. So sine is y over r again. R is 1. What's y at this angle position? 3 pi over 2. What's this y value right here?
-1.
So -1 over -1 is -1. So that's right here. Is that okay?
Yeah.
3. 2 times 3 is 6. 6 minus 1, 5. 5 pi over 2. So now we're just starting to see a pattern. 1 pi over 2, 3 pi over 2, 5 pi over 2, and it'll be 7 pi over 2, like that. Where's 5 pi over 2? So this is 0, 1 pi halves, 2 pi halves, 3 pi halves, 4 pi halves, 5 pi halves. We're right back up here again. Well, we're coterminal in the same angular position as 1 pi halves. And what did we get for sine of pi halves? We got
1.
1. So this is also going to be 1. 1. 4. 2 times 4 is 8. 8 minus 1 is 7. 7 pi over 2. That's why that first step that we always talk about is so crucial. 7 pi over 2 is 1, 2, 3, 4 pi over 2, 5 pi over 2, 6 pi over 2, 7 pi over 2 is right here, which is coterminal with 3 pi over 2. So the sign is the same answer as 3 pi over 2, which was the negative 1. Is that okay?
Yes.
Yes.
So what's going to keep happening here? It's simply going to be 1, negative 1, 1, negative 1 forever, isn't it?
Mm-hmm.
Yes.
What kind of graph would that be?
A sine curve?
Oscillating.
It's oscillating, good. If we connected, Josh, as a function, it would be the sine curve, good. But for the terms of the sequence only, it's simply
Oscillating.
oscillating from 1 to negative 1. At n equals 1 is 1. At n equals 2, it's negative 1. N equals 3 is so so that first step is always this. What's the limit of, as you go out forever, of the individual terms of the sequence? If it converges to 0, well, then we have a chance for the sum to converge and we continue to explore. But if this does not converge to 0, well, then there's no chance when you add them up forever that it could converge. So what is the limit of this individual terms of the sequence? Are they, they are alternating, but are they alternating closer and closer to 0?
No.
No.
So are they alternating going out to infinity on half of them and negative infinity on the other half of them?
Yes.
Or is it alternating to the same number but positive and negatively? Isn't it 1 and negative 1 forever? This is never going to go down, Josh, to negative infinity. It's just going to keep being 1, negative 1, 1, negative 1 forever. Is that okay?
Yeah.
Yeah.
So this diverges for which one of the reasons? Because the terms go to infinity? Because the terms go to negative infinity? They're alternating between negative and on one half, they're going up closer to infinity and the other half down to negative infinity?
So
Or because they're alternating?
does
Okay, go
that
ahead.
mean does that mean that the limit doesn't exist?
Yes. Mhm.
Okay.
Alternating between negative 1 and 1, which means the limit does not exist. And it's for what reason? Not because you get infinity only or negative infinity only, but because it's oscillating or alternating from 1 to negative 1 forever. Is that okay?
Yes.
And this is not equal to 0. So what does that mean then when we start to add up these terms forever? Is there any chance that they could converge?
No.
No. So do we need to go and explore any further and use one of the series tests, or are we done already?
We're done.
We're done. Therefore, the series, well, let me just write it up here. Therefore, this series diverges. It has no chance to converge. Why not? Because the individual terms did not converge to zero. Using, what's the language we can say? What happened using the what?
Alternating series test.
Did we get past the first step, Josh? Did we get that the individual terms of the sequence converge to zero? Did we get to that first? Did we get to that first step, or did it equal to zero or not equal to zero?
It did not.
It did not. So then there's no chance that these, when you add up these individual terms, that it could converge. So there's no opportunity for us to explore further and use the geometric series test or the integral series test or the p-series test or the alternating series test. We don't even have to get there because this first step that we always check, the limit of the individual terms as you go forever does not equal zero. If you, well, let me leave it at that, okay? Using the nth term test or divergence. Question? Denise, question? Are you confused on something?
Nope.
Josh?
No.
I know you're probably exhausted, and one thing that a person could be thinking is when we said ignore the positive and negativeness, well, if you did that, then these would all just be ones. And these are not getting closer and closer to zero either, are they?
No.
No. So remember, when we say ignore the positive or negativeness on the first step, that's just because if we're kind of confused and we want to say, okay, are these terms getting closer and closer to zero or not? Well, the first thing is, the best thing is just to look at the values, and it's 1, -1. So that in itself should be enough. 1, -1. 1, -1. It's just going to keep alternating forever, and there's no way these are going to converge to zero. Done. If you wanted to take the limit formally, of the individual terms, formally, which means computationally, well, you can't unless you ignore the negative part. And well, even on this one, it's not really possible because this is a sign. It's not like you can just, if you put infinity in right here, 2 times infinity is infinity, infinity minus 1 is infinity, infinity times pi is infinity, infinity divided by 2 is infinity, and sine of infinity well, the sine graph just goes up and down forever, so this would diverge. If you did this formally, I guess we could, and you would get diverge by the oscillating type. So if you look at the first step, the individual terms are alternating from 1 to -1, so there's no chance that they're getting closer to 0, which means there's no chance when you add them up forever that they could converge. So you're done by the nth term test for divergence, and that's sort of visually. If you tried to do the first step formally and you took the limit of this formula as n approaches infinity, like this, and we plugged in infinity, we get sine of infinity, but we know the sine graph just goes up and down forever. And so when you go out to infinity, this just oscillates forever and it's not getting closer to any finite single number. So you could then, formally, you could say it diverges by oscillation, and then you're still done by the nth term test for divergence. So I don't know what else to say. So any questions or comments there?
No.
No.
So here we're going to put diverges. And that's it. It seems kind of cheap here. You can just put a dot. You can just fill in a bubble, and then either you're right or wrong. And this one I want you guys to try, and you're going to just write out the first few terms, put 1 in, put 2 in, and see what happens, okay?
Mhm.
And I'm just trying to think in my mind. Yeah, so no, this one you really should not have any difficulty with if you just write out the first few terms and do what we were doing, just like this one or any of the other ones, okay?
Okay.
Okay, so, all right. So that's it for today. I know it, once again, incredibly long. For whatever it's worth, I got an email from one of your classmates last night. And I guess he has a friend who's with another class at another campus, and they're not, they're just being given the assignments and they're not getting any help at all. No, and they're just supposed to go and look. I guess they can go to these Read It and Watch It and everything like that, or anywhere else on the internet, but that's gotta be tough. So I don't know. This is really long, and that's also tough. And the other way is tough too. Or even if I picked something in the middle and only talked for an hour and a half, and even then it would be tough. It's just, I don't know what else to do. Because now I feel like I've given everyone a fair chance to do these problems. And they may or may not get them, but I think I've given them, I've told them everything they need to know. They may get stuck, but they may not. So I hope you guys understand, and I thank you for your patience. And if you need any help, I'll be available tomorrow at 10:50 and also on Friday from 10:50 to 11:20 as well, okay?
Okay.
Just hang in there, be strong. You're gonna have another quiz yet. I'm gonna put a quiz out on sections 9.1 to 9.3, which we just finished today. 9.5 is the new section today. That won't be on your quiz. Next week is our last regular week, and we will certainly, without a doubt, well, I guess there's always a doubt, but more than likely we will do 9.6 and 9.4, and that's probably where we'll stop, unfortunately. Wish we had a couple more weeks. I'm sure you do too, and then we could get the last sections done, but we don't. So, but that's, again, if you continue in Calculus 3, you're gonna be fine. So anyway, okay guys, anything else before we stop?
When did you say the quiz is gonna be put up?
Oh, I didn't. So let me say It'll either be today or for sure tomorrow sometime, okay?
And how many days do we have to get it done?
Oh, so today is Wednesday. I'll give you 5 days to do it. So yeah,
Okay.
okay. And then you're gonna have one more test over these sections in chapter 9 that we will do. So it'll be 9.1 to 9.6, okay?
Okay.
Okay, guys. Well, thank you again, and take care. Get some rest. Go get to have a break, and have a nice day.
Mr.
Okay.
Mr. King, I'm sorry. You said we have one more test. So when's the final?
Oh, well, then there's the final as well. Yeah.
Okay.
So the final exam will be in 2 weeks. Is final exam week, and then I'm gonna do is give the class the freedom to choose, as long as it's done, it has to be done by, let's see here. I'll say Thursday night on final exam week. The WebAssign will kick anyone out by 11:59 p.m., but that's when it'll be due. No later than that day, but then it'll be open. I'll put it in there Sunday, or maybe if not Sunday, then for sure Monday. Okay.
Okay.
Final exam week. I want to think about that. If I'm supposed to technically, I think officially I'm not supposed to put it in there until Monday. But if that means 12 o'clock on Sunday midnight, Sunday night, well, then that's okay too.
Okay.
All right.
Okay.
Okay. Anything else, guys?
No, sir.
No.
Okay. Well, thank you and take care, and we'll talk to you soon. Okay.
Thank you. Bye.
Have a good day.
Goodbye.